Most people think they know what the Milky Way is: a band of light in the sky, a spiral galaxy, a place we live in and rarely think about. But here's the quiet truth. We've never seen the Milky Way from the outside. We don't know exactly how big it is. We don't know where it truly ends, and we don't understand most of what it's made of. Everything we know comes from inside it, from one small star system drifting through a galaxy that's been changing for billions of years without noticing us at all. This isn't a lecture, and it isn't a list of facts. It's a walk through the galaxy we call home, what we know, what we've discovered recently, and what still doesn't make sense. As you listen, there's one thing I'd genuinely like to know from you. When you think about the Milky Way, what fascinates you the most? You can share that in the comments whenever it crosses your mind. For now, just stay here, because once you realize how little of the Milky Way we truly understand, it becomes clear that we're not standing still beneath the stars, we're moving with them. And this story begins exactly where you are, inside the galaxy itself. When people imagine the Milky Way, they usually picture a clean spiral shape floating in space, glowing softly, perfectly balanced. But that image isn't a photograph, it's a model, a reconstruction, a best guess based on limited information, because there's something important we can't do. We can't step outside our own galaxy to see it. Every observation we've ever made comes from inside the disk, from one ordinary star system located far from the center. It's like trying to understand the shape of a forest while standing between the trees at night. That's why so much of the Milky Way is still uncertain. We know it's huge. Light would take over 100,000 years to travel from one side to the other, but even that number keeps changing as we discover fainter stars and distant structures farther out than we expected. And here's something most people don't realize. Almost everything you can see in the night sky, every star, every glowing cloud, adds up to only a small part of the galaxy's total mass. Most of the Milky Way doesn't give off light at all. It doesn't shine. It doesn't glow. It doesn't show up in telescopes. We only know it's there because of gravity, because stars move as if something invisible is holding them in place. Scientists call this invisible matter dark matter, but that name doesn't really explain anything. It's just a label for something we don't yet understand. Without it, the galaxy would fly apart. Stars would drift away. Spiral arms wouldn't hold their shape. The Milky Way wouldn't exist in any stable form. So, in a very real sense, the part of the galaxy we understand least is the part doing most of the work. And while all of this sounds distant, it's happening right now, around you. The Earth is moving around the Sun. The Sun is moving around the center of the galaxy, and the galaxy itself is moving through space, pulled by gravity from other galaxies nearby. You don't feel any of it because everything around you is moving together. Motion at this scale feels like stillness from the inside. That illusion of stillness makes the Milky Way feel permanent, almost frozen in time, but it isn't. Stars are constantly being born and dying. Massive clouds of gas slowly collapse, ignite, and eventually scatter their material back into space. Over millions of years, the galaxy stretches, bends, and reshapes itself. Even the spiral arms aren't fixed structures. They're more like slow traffic jams, areas where stars bunch up briefly before continuing on their way. Our solar system is passing through one of those regions right now. We weren't always here, and we won't stay here forever. At the center of the Milky Way sits something much heavier than everything else around it, a supermassive black hole called Sagittarius A star. It's millions of times more massive than the Sun, yet it's surprisingly quiet most of the time. Still, the galaxy carries scars from its past. Huge bubble-shaped structures rising above and below the galactic center suggest that long ago the core released enormous bursts of energy. The Milky Way hasn't always been calm. It has gone through violent phases, collisions, and periods of intense activity. It has also grown by taking in smaller galaxies. Over billions of years, the Milky Way has slowly pulled apart neighboring galaxies, absorbing their stars into its own structure. Some of the stars you can see tonight didn't form here at all. They're leftovers from galaxies that no longer exist as independent systems. Even more quietly, the atoms in your body were forged in stars that lived and died long before the Milky Way fully took shape. And despite all of our technology, space telescopes, satellites, supercomputers, we still don't know some of the most basic facts about our galaxy. We don't know its exact mass. We don't know where its true edge is. We don't know what dark matter actually is. We don't even know how common galaxies like ours really are. The Milky Way feels familiar because we live inside it. But familiarity doesn't mean understanding. From within, something enormous can feel ordinary. And that's the quiet truth at the start of this story. We don't fully understand the galaxy that carries us through space. We never have. And as we move deeper into it, that uncertainty becomes part of the journey itself. We live on a planet that circles an average star. That star sits in a quiet neighborhood of the Milky Way, nowhere near the center, nowhere near the edge, just off to the side. About 2/3 of the way out. That detail matters more than it sounds. The center of the Milky Way is crowded, dense, chaotic. Stars packed close together, intense radiation, frequent stellar explosions. It's not a friendly place for long-term stability. Planetary systems there are constantly disturbed, pulled, or disrupted. The outer edges, on the other hand, are thin and sparse. Fewer heavy elements, fewer materials needed to build rocky planets like Earth. We're in between. Astronomers sometimes call this region the galactic suburbs. Not exciting, not dramatic, but stable. Our Sun sits inside a spiral arm known as the Orion Arm, or sometimes the Orion Spur. Even the name tells you something important. It's not one of the galaxy's main arms. It's more like a smaller offshoot, a partial structure. That's another misconception people often have. We don't live in one of the Milky Way's major spiral arms, and we're not near the center of anything. We're just somewhere that worked. From here, it's easy to assume the galaxy is neatly organized, but when astronomers began mapping star positions and motions more precisely, that idea started to fall apart. The Milky Way isn't symmetrical. Its disk is warped. Its arms aren't evenly spaced. Some stars move in ways that don't match the galaxy's rotation. It's less like a perfect spiral and more like a living system that grew unevenly over time. And because we're inside it, our view is limited. Gas and dust block large portions of the galaxy from our sight, especially toward the center. Entire regions are hidden behind thick clouds that absorb visible light. For a long time, astronomers thought those areas were simply empty. They weren't. They were just obscured. Only when we started observing the galaxy in infrared, radio waves, and other non-visible wavelengths did those hidden regions begin to appear, and with them came surprises, unexpected star clusters, strange motions, structures that didn't fit older models. This means something important. Every map of the Milky Way you've ever seen is incomplete, even today. And our position inside the disk adds another complication. The galaxy isn't flat like a record. It bends, it ripples. One side dips slightly up, the other slightly down, as if something tugged on it long ago. Most likely something did. Past encounters with other galaxies distorted the Milky Way's shape, and those distortions never fully went away. They're still there, frozen into the structure, slowly rotating with everything else. From our location, we're also shielded. The dense gas near the center blocks certain types of radiation from reaching us. Our distance from the core reduces exposure to violent events like frequent supernovae, and our position relative to nearby stars lowers the chances of close gravitational disruptions. In other words, where we are isn't special because it's central, it's special because it's quiet, and quiet is rare in a galaxy this large. Still, even here, nothing is fixed. The Sun completes one orbit around the Milky Way roughly 225 to 250 million years. During that time, it passes through different regions, different densities, different environments. The sky above Earth has changed many times over its history, and it will continue to change long after we're gone. Stars drift, neighbors come and go, constellations stretch and fall apart. The galaxy does not revolve around us. We are simply moving with it. And that's the key idea to hold on to as we go deeper. We're not standing still, observing the Milky Way like an object. We're embedded inside a system that's constantly shifting around us. Understanding the galaxy means letting go of the idea of fixed positions and permanent structures, because in the Milky Way, everything is in motion, even the places that feel calm. And next, as we continue, we'll talk about scale, not the kind that fits on a chart, but the kind that quietly breaks intuition. Because once you understand just how large the Milky Way really is, it becomes clear why almost everything we think we know about it comes with uncertainty. When people hear numbers like 100,000 light-years, they tend to stop listening. The number is too big to picture, so the mind treats it like background noise, something impressive but abstract. That's a problem, because size explains almost everything about why the Milky Way is so hard to understand. A light year isn't time, it's distance. It's how far light travels in 1 year, about 6 trillion miles. Even that number doesn't help much, it's still too big. So here's a simpler way to think about it. If light left the center of the Milky Way at the moment the first human tools were being shaped on Earth, that light still wouldn't have reached the far edge of the galaxy today. That's how wide it is. And even that might be an underestimate. For a long time, astronomers thought the Milky Way ended where the bright stars stopped. Beyond that, they assumed there wasn't much else. They were wrong. Over time, as instruments improved, they began detecting faint stars far beyond the visible disk. Then came the discovery of a massive, invisible halo surrounding the galaxy, a vast spherical region dominated by dark matter and sparsely populated with stars. This halo extends far beyond the spiral arms, much farther than the glowing disk most people picture when they think of the Milky Way. In fact, if you include the halo, the Milky Way may span more than 1 million light-years across. That means the part of the galaxy we can see is only a small island inside something much larger. And size doesn't just mean width. The Milky Way is thick. The central region bulges upward and downward, packed with stars. The disk itself has layers, older stars drifting above and below the main plane, younger stars closer to the center line, gas clouds clumped unevenly throughout. From our position inside the disk, this thickness is hard to notice. We mostly see the galaxy edge on, as a bright band stretching across the sky. But that band isn't a line. It's depth stacked on depth, stars layered behind stars, clouds behind clouds, distances overlapping in ways that our eyes can't separate. This overlapping is one reason why distance measurements inside the galaxy are so difficult. Two stars can look close together in the sky, but be tens of thousands of light-years apart.
Others can look faint, not because they're small, but because they're buried behind dust. So when astronomers say how big the Milky Way is, they're often giving a range, not a precise figure. And that uncertainty grows as you move outward. The farther from the center you go, the fewer reference points there are, fewer stars, less light, more darkness. At the outer edges, stars orbit more slowly than expected. Their motion doesn't match the gravity of the visible matter alone. This was one of the earliest strong clues that something unseen was adding mass to the system. That unseen mass stretches far beyond the visible galaxy, shaping the motion of stars even where there's almost nothing to see. So the Milky Way isn't a clean boundary. It fades, it thins out, it dissolves gradually into intergalactic space. And because of that, defining its edge depends on what you choose to measure: light, gravity, or motion. All of them tell slightly different stories. There's also the issue of time. When we look across the galaxy, we're not seeing it as it is right now. We're seeing it as it was in the past at many different moments, all at once.
Light from nearby stars is relatively recent. Light from distant regions left long before humans existed. So the Milky Way we observe is a layered record of its own history, stretched across space. That means there is no single current image of the galaxy. By the time light reaches us, the galaxy has already changed. Stars have moved, gas clouds have shifted, explosions have happened and faded. This is another reason why certainty is hard to come by. The Milky Way is too large to capture in a single moment, and too complex to summarize with a single number. And yet, despite all this uncertainty, one thing is clear. We live deep inside something enormous, so large that even our best measurements come with margins of error measured in tens or hundreds of thousands of light years. Understanding that scale doesn't make the galaxy feel more dramatic, it makes it feel more distant, more patient, less concerned with small details, including us. And next, we'll talk about the invisible structure that makes all of this possible, the hidden mass that gives the Milky Way its shape, its stability, and much of its mystery. If the Milky Way were made only of the stars and gas we can see, it wouldn't look the way it does. It wouldn't rotate the way it does either. This was one of the first clues that something was missing. When astronomers measured how fast stars orbit the center of the galaxy, they expected stars farther out to move more slowly. That's how gravity usually works. Less mass inside the orbit means weaker pull. But that's not what they found. Stars far from the center were moving too fast, fast enough that they should have escaped the galaxy entirely. And yet they didn't. Something was holding them in. That something doesn't give off light, it doesn't absorb it, it doesn't reflect it, it doesn't behave like any normal matter we know. We only know it exists because of its gravity. This is what we call dark matter. The name sounds dramatic, but it's really just a placeholder, a way of saying there is mass here and we don't know what it is. Dark matter doesn't sit in one place. It forms a vast halo around the Milky Way, extending far beyond the visible stars. This halo is what gives the galaxy its overall shape and stability. You can think of the bright spiral disk as a thin layer resting inside a much larger invisible structure. Without that structure, the disk would unravel. Stars would drift away. Spiral arms would dissolve. The galaxy would slowly come apart. Instead, everything stays bound together, orbiting calmly over billions of years. What makes dark matter especially strange is how little it interacts with anything else. It doesn't collide the way normal particles do. It passes through stars, planets, and people without leaving a trace. Right now, countless dark matter particles may be passing through your body every second, completely unnoticed. That idea sounds unsettling at first, but it's harmless.
Dark matter doesn't stick, it doesn't accumulate, it simply moves through, guided only by gravity. And here's another detail that often gets overlooked. Dark matter likely existed before the Milky Way formed. Long before stars ignited, dark matter had already begun clumping together under gravity, forming the framework that ordinary matter later fell into. Gas followed the gravitational wells created by dark matter, cooled, collapsed, and eventually lit up as stars. In that sense, the Milky Way didn't form randomly. It formed where dark matter told it to. Even now, dark matter continues to influence the galaxy's behavior. It affects how stars move, how the disk warps, and how the galaxy responds to interactions with its neighbors. But even after decades of study, we still don't know what dark matter is made of. It could be an undiscovered particle. It could be something more exotic. It could even force us to rethink how gravity works on large scales. Different experiments are looking for it in different ways: deep underground detectors, particle accelerators, space-based observations. So far, nothing has given a definitive answer. And that uncertainty matters, because if we don't understand the majority of the galaxy's mass, we don't fully understand the galaxy itself. The Milky Way we see is just the surface. The real structure, the one doing most of the work, is invisible. And that leads directly to the next layer of the story. At the center of this massive system, embedded deep within both visible and invisible matter, lies an object so dense that space and time behave differently around it. A single point that influences the motion of stars thousands of light years away. At the center of the Milky Way, something extremely massive sits in one place. Not at the exact middle of the stars you see in the sky, but at the gravitational center, the point everything else slowly moves around. For a long time, astronomers suspected it was there without being able to see it. Stars near the center moved too fast, following tight curved paths as if they were orbiting something invisible and incredibly heavy. Over years of careful observation, those star paths were mapped in detail. Their motion left only one possible explanation: a supermassive black hole. It's called Sagittarius A star, and it has a mass millions of times greater than our Sun, packed into a region smaller than our solar system. Despite its size, it's quiet. It isn't constantly pulling stars in. It isn't tearing the galaxy apart. For most of its existence, it simply sits there, influencing its surroundings through gravity alone. That calmness is important to understand because black holes are often imagined as violent, constantly feeding objects. In reality, most of them spend long periods in a low activity state. Sagittarius A star is one of those. From Earth, it's hidden behind thick clouds of gas and dust that block visible light. We only detected it by watching how nearby stars move, and by observing radio and infrared signals that can pass through the obscuring material. Those observations revealed something else. The center of the Milky Way is crowded, stars are packed tightly together, orbits are fast and complex, gravity there is intense. A star can complete an orbit around the central black hole in just a few years, something that would take our Sun more than 200 million years to do around the galaxy.
Time itself behaves differently close to such a massive object. According to relativity, clocks near the center would tick slightly slower than those farther out. The effect is small on human scales, but it's real. Even so, the black hole is not the most dramatic thing in the region. The surrounding environment is full of energy. Powerful magnetic fields, dense star clusters, and streams of hot gas interact in ways that are still being studied. It's one of the most complex and active regions of the entire galaxy. And the galaxy remembers that it was once even more active. Huge structures called the Fermi bubbles extend tens of thousands of light years above and below the galactic center.
They're made of high-energy particles, and they suggest that in the past, Sagittarius A star released enormous amounts of energy. Not recently, but not impossibly long ago either. On cosmic timescales, these events were fairly recent. This means the calm we see today is not guaranteed forever. The black hole can become active again if enough material falls toward it. When that happens, it can affect large regions of the galaxy. That doesn't mean it's a threat to Earth. We're far enough away that even a strong outburst would likely be more of a cosmic light show than a catastrophe. But it does remind us that the Milky Way center is not static. It has a history, and it has influence. The gravity of the central black hole helps organize the inner regions of the galaxy. It affects star motion, gas flow, and the overall balance of the system. But it doesn't control everything. The Milky Way is too large, too massive, and too complex to be dominated by a single object, even one as extreme as a supermassive black hole. Instead, the galaxy is shaped by layers of influence: dark matter on the largest scales, gravity from billions of stars in the disk, and intense forces near the core. All of these layers interact quietly over very long periods of time. And while the center feels distant and abstract, its past actions are written into the structure of the galaxy itself. It's easy to think of the Milky Way as a finished thing, something that formed long ago, settled into place, and has been quietly spinning ever since. But that picture isn't accurate. The galaxy we live in is not complete. It's still in the middle of becoming what it will be. Change in the Milky Way doesn't happen quickly. It happens on timescales so long that they barely register to the human mind. But slow doesn't mean inactive. Stars are still forming right now. Deep inside cold, dark clouds of gas, gravity slowly pulls material together. As the clouds collapse, they heat up, pressure rises. Eventually, nuclear fusion begins, and a new star turns on. This has been happening for billions of years, and it hasn't stopped. At the same time, other stars are reaching the end of their lives. Some swell into red giants and gently shed their outer layers back into space. Others explode as supernovae, scattering heavy elements across the galaxy. Those elements, carbon, oxygen, iron, become the raw material for future stars and planets. The Milky Way is constantly recycling itself. Nothing here is wasted. Everything moves on to the next stage. Even the spiral arms are temporary features. They aren't solid structures made of the same stars forever. Stars drift in and out of them as they orbit the galaxy. The arms are more like slow-moving density waves, places where gas and stars pile up briefly before continuing on their paths. Our solar system is passing through one of these regions right now. Millions of years ago, we were somewhere else. Millions of years from now, we'll be somewhere else again. The galaxy also changes shape. It bends and warps, especially toward its outer regions. The disk isn't perfectly flat. One side curves slightly upward, the other downward, like a warped sheet. These distortions didn't appear randomly. They're likely the result of past interactions, gravitational nudges from smaller galaxies passing nearby, or material falling into the galaxy at odd angles. Those interactions never fully stop. Even now, the galaxy is responding to forces beyond itself. The stars don't all move in perfect circles either. Some follow tilted orbits. Others move faster or slower than expected. Groups of stars share common motions, suggesting they were born together or arrived from an external source. When astronomers map these motions in detail, they see patterns, ripples moving through the disk, as if the galaxy were struck long ago and never fully settled. This is what makes the Milky Way feel less like a machine and more like a living system, not alive in the biological sense, but dynamic, responsive, shaped by its past and still adjusting to it. And this ongoing change has consequences. Regions that were once calm can become active. Star formation can flare up in one area and fade in another. The conditions for planets and possibly life shift over time. The Milky Way today is not the Milky Way of the distant past, and it won't be the Milky Way of the distant future. This matters because it means we are living in a particular moment, not at the beginning, not at the end, but somewhere in the middle of a long story. From a distance, galaxies can look isolated, like separate islands floating in space, but that's not how the universe is arranged. Galaxies live in neighborhoods.
Astronomers have found many of these stellar streams. They're the remains of galaxies that were torn apart over billions of years. Their stars now move through the Milky Way, mixed in with our own, often indistinguishable unless their motion is studied carefully. This means the Milky Way has grown by consuming others. It didn't form in isolation. It built itself gradually, piece by piece, through a long history of mergers and interactions. Some of the stars near us may not have formed here at all. They could be immigrants, captured long ago and now fully integrated into the galaxy. Even the structure of the Milky Way reflects this past. Its halo contains stars moving in odd directions, at odd speeds, suggesting they came from different origins. The warp in the disk, the ripples in star motion, and the uneven distribution of material all point to past encounters. And these encounters aren't over. Several small galaxies are currently orbiting the Milky Way, slowly losing stars as gravity pulls them apart. Over time, they too will be absorbed. From the inside, this process feels invisible. The night sky looks calm, the stars appear fixed. But on larger timescales, the Milky Way is quietly reshaping itself through these interactions. This kind of growth isn't unusual. Most large galaxies we observe show signs of past mergers. It's a common way galaxies evolve. They grow by drawing in what's nearby, guided by gravity alone. And while this sounds destructive, it's also creative. Mergers bring in fresh material, gas that can fuel new star formation, stars with different chemical histories, and momentum that stirs the galaxy into new patterns. Without these interactions, the Milky Way would be smaller, quieter, and less complex. But the most significant interaction in our future isn't with a small galaxy, it's with a large one. Andromeda is the nearest large galaxy to the Milky Way. On clear dark nights, it's actually visible to the naked eye, a faint smudge of light far beyond our own stars. That soft glow represents trillions of stars, all bound together in a system similar in size to our own. Andromeda isn't sitting still, it's moving toward us. At about 70 miles per second. That sounds fast, but on cosmic timescales, it's unhurried. The encounter is still billions of years away. Long after the sun has changed, long after human history has ended. When people hear that the Milky Way and Andromeda are going to collide, they often imagine chaos, stars smashing into each other, planets being flung into space. That's not what will happen. Galaxies are mostly empty space. The distances between stars are so vast that direct collisions are extremely unlikely. Instead, what will happen is something slower and more subtle. Gravity will take over. As the two galaxies approach, their shapes will begin to distort. Spiral arms will stretch and twist. Streams of stars will be pulled outward, then folded back in. Over time, the two systems will pass through each other, not once, but several times. Each pass will drain energy from the system, slowing the galaxies down, drawing them closer together. Eventually, they'll merge into a single larger galaxy.
By that time, the familiar spiral shape of the Milky Way will be gone. The new galaxy will likely be more rounded, with stars moving in many different directions. From the inside, the night sky would look very different. And yet, even during the merger, most star systems would remain intact. Planetary orbits would mostly survive. The biggest changes would be in the sky itself. New constellations, shifting star fields, and a bright, sprawling glow where Andromeda once was. This kind of merger is not unusual. Astronomers see galaxies in every stage of this process across the universe. It's part of how galaxies grow and change over time. And it's not the end of the story. Even after merging with Andromeda, the new galaxy will continue to interact with others. Gravity doesn't stop working just because two systems combine. The local group itself may eventually merge into an even larger structure, drawn together by the mass of surrounding galaxies and dark matter. On these scales, the universe is still sorting itself out. The future of the Milky Way isn't destruction, it's transformation. And that idea carries through to smaller scales as well. Because even without dramatic mergers, the galaxy is constantly revealing structures we didn't know were there, features hidden in plain sight, only recently uncovered. For most of human history, the Milky Way looked simple, a bright band
Find a
across
comfortable
the
spot,
sky, a
relax,
scattering
and
of
let your mind
stars,
drift among the
nothing
stars
more.
with me.
Even after telescopes improved, the picture stayed roughly the same. A
Just
disk,
imagine on a
spiral
clear,
arms,
dark
a
night,
dense center,
far away from the
clean,
city lights, you look
understandable.
up. You see a faint,
That sense of
luminous band
simplicity
stretching
didn't
across the
last.
entire
As
sky.
instruments
That
became more
beautiful,
sensitive,
milky river of light
astronomers
is our
started
galaxy,
seeing things
seen
that
from the
didn't fit
inside.
the older
It's a
models,
breathtaking
faint
sight,
structures,
isn't it?
strange
A reminder
shapes,
of just
patterns
how
that
vast
only
our
appeared
cosmic
when
home
data
truly
from
is.
many wavelengths
The name
was
Milky Way
combined.
comes from the ancient
One of the
Greeks,
biggest
and for
surprises
centuries,
came from the
that's what it
center of
looked
the
like, a
galaxy.
soft, ethereal
Above and
cloud.
below
It wasn't until
stretching
Galileo
tens of
Galilei
thousands
pointed
of
his
light
telescope
years
at
into
it in
space,
1610 that we
scientists
realized
discovered
this Milky
enormous
Band was
bubble-shaped
actually made of
regions
countless
filled with
individual
high-energy
stars, each
particles.
one a distant
They're
sun.
now known
So,
as the Fermi
what
bubbles.
exactly is the
They
Milky
don't
Way?
glow in
It's a
visible
barred
light.
spiral
They
galaxy.
show up in
Let's
gamma
break that
rays,
down.
the most
A spiral
energetic
galaxy
form
has a
of light
central
we can
bulge, a
observe.
flat, rotating
These
disk of
structures
stars,
weren't
gas, and
predicted.
dust,
They weren't
and
expected.
beautiful spiral
And they
arms
imply
winding
that the
out from the
center of the
center.
Milky Way
Our
was
galaxy
far
has a
more
special
active in the
feature,
past
a
than it is
bar-shaped
today.
structure of stars running
Something
through its core.
injected a
From this
huge amount
bar,
of energy
our spiral
into the
arms
galaxy
emerge.
long ago,
Think of it like a
and the
cosmic
evidence is
pinwheel
still there,
spinning gently
slowly
through
fading.
space. Our galaxy
Another
is
surprise
enormous.
came from
It's
mapping
about
stars in
100,000
detail.
light years
When
across.
astronomers
A light
began
year is the
tracking
distance
the
light
precise
travels in
motions
1
of
year,
millions
which
of
is nearly
stars,
6
they
trillion
noticed
miles.
long, narrow
So,
streams
if you could
moving
travel at the
together
speed of
through the
light,
halo.
it would still
These
take you
weren't random
100,000
alignments.
years
They
to
were
cross
the
from one
stretched
side of the
remains
Milky
star
Way to the
clusters
other.
and small
It's
galaxies
almost
torn apart
impossible
by
to
gravity.
truly grasp that scale.
These streams
Within this
wrap
immense
around the
structure,
Milky Way
there are
like
anywhere
faint
from
ribbons,
100 billion to
marking
400
ancient
billion
paths of
stars.
destruction
Our
and
Sun is
absorption.
just one of them,
They tell a
and
story
many of
the
these
visible
stars, like
galaxy
our Sun,
doesn't
have
show on
planets
its own.
orbiting them.
The
Astronomers
Milky
now
Way
believe there
also
could
has
be
a
billions of
bar-shaped
planets in our
structure at its
galaxy
center,
alone,
a
with a
dense
significant
region of
number
stars
potentially
that cuts
being
through
rocky
the
and
core.
Earth-sized.
For a long
Located
time,
in the
its
habitable
size,
zone of their star,
orientation,
the
and
habitable
influence
zone
were
is that
unclear.
sweet spot where conditions
New
might
data
be just
revealed that
right
this bar
for liquid
is
water to
larger and
exist
more
on a planet
complex than once
surface.
thought. It rotates. It funnels gas inward.
Our solar system
affects
is
star
located in one of the
formation
Milky
across
Way's
wide
smaller
regions of the
spiral arms,
galaxy.
known as the
Then
Orion
there are the
Arm,
magnetic
or the
fields.
Orion Spur.
They're invisible, but they thread through the Milky Way, shaping the movement of charged particles and influencing how
The center
gas
of the
clouds
galaxy
collapse.
is a very busy,
These
very
fields
chaotic
stretch
place.
along
At the
spiral
very heart of
arms,
the Milky
twist
Way
near
lies
the
a
center,
supermassive
and
black
extend
hole.
into the halo.
It's incredibly far away,
Only recently
and its
have
gravitational
astronomers
pull
begun to map
keeps the
them in
galaxy
detail.
spinning and holds
Each
everything
new map
together. This
reveals
black hole
structure
has a mass
layered
of
on
about a
structure,
million times that of our
complexity
Sun,
built over
all packed into an
billions of years.
incredibly tiny
And this
space.
process
It's a
isn't
silent,
finished.
invisible
With
giant,
every new
anchoring our
survey,
entire
the
galactic
galaxy
home.
becomes less
Now,
tidy and
let's
more
drift through
interesting.
those beautiful spiral
Features once
arms.
thought smooth
The Milky
turn
Way
out
is thought
be
to have for
clumpy.
main arms
Regions
the Perseus
assumed
arm,
empty
the Scutum
reveal faint
Centaurus arm, the
populations of
Norma arm,
stars.
and the Sagittarius
Even the
arm.
number of
These arms are
spiral
not
arms
solid
is still
structures.
debated.
They are more
Some
like
models
cosmic
show
traffic
4
jams,
major
areas of
arms.
higher
Others
density
show
where
2
gas and
dominant
dust are
ones with
compressed.
smaller
This
offshoots.
compression triggers
The
bursts of
truth
star
depends on
formation,
how you
so
define
the
an
spiral
arm and
arms are
which
where the
type of
newest,
stars you
brightest,
track.
bluest
This
stars are born.
ongoing discovery
They are the
matters for
galaxy's
one
stellar
reason.
nurseries,
It shows
glittering
us
with the
that the
light of
Milky
young
Way is
suns.
not a
Our
simple
galaxy
object
isn't
we've
just a
already
flat
figured
disk.
out.
It's surrounded
It's a
by a
system with
vast,
hidden layers
spherical
that
cloud
only
called the
become
galactic
visible
halo.
when we look in new ways. And many of those layers are directly
But the
tied
visible
to
parts
danger,
of the galaxy, the
to
stars, the
environments where
gas,
life would
the dust
struggle
are
to survive.
only a tiny fraction of its
From
total
where we
mass.
are, the
Most of the Milky Way
feels
is
calm.
made of something
The
we
night
can't see at
sky
all,
changes
dark matter.
slowly.
We can't detect it
Stars
directly,
rise
but
and
we know
set.
it is there because we
Nothing
can see its
seems
gravitational
urgent.
effects on the
That
stars and
sense of
gas we
peace
can
comes
see.
from location,
This mysterious
not from the
substance
nature
forms a
of the
massive halo
galaxy
around our
itself.
galaxy,
Many
far
regions
larger
of
than the
Milky
visible
Way are
halo.
hostile
It's the
by
invisible
default.
scaffolding that holds our
Closer to
galaxy
the
together.
center, stars are
Without dark
packed
matter,
tightly
the
together.
stars on the outer
That
edges of the
density
galaxy would be
increases the
flying off
chances
into
of close
space.
encounters.
Our Milky Way
Stars
isn't
passing near
alone
each
in the
other,
universe.
disturbing
It's
planetary
part of a small
systems,
collection of
altering
galaxies
orbits,
called the
or
local group.
stripping
Our
planets
biggest
away
neighbor is the
entirely.
Andromeda Galaxy,
Radiation
another
levels
beautiful
there
spiral
are higher
galaxy about
too.
2.5 million
Supernovae
light
happen
years
more
away.
often. Energetic events that are rare in our neighborhood are common closer in.
And
Move
here's
even
something
farther
exciting.
inward, and
The Milky Way
environment
and
becomes
Andromeda are
extreme.
on a collision
Near the
course.
central black
They are
hole,
hurtling towards
gravity
each
is
other at about
intense.
70
Gas
miles per
clouds are
second.
heated
But there's
and
no need to
compressed.
panic.
High
This
energy
cosmic merger
particles
won't happen
flood
for
the
another
region.
4.5
Any
billion
stable,
years.
long-lasting
When it does,
planetary
it will
system
be a
would have
slow,
hard
graceful
time
dance.
surviving.
The galaxies
But
will
danger
pass through
isn't
each other,
limited to
their
the
stars
center.
mostly missing
Some
each
regions
other
of the
because
galaxy
space
are
is
shaped
so
by
vast.
massive stars.
Over hundreds of
Stars
millions
that
of
live
years,
fast
gravity
and
will
die
pull them together,
violently.
and they will merge to
These
form a
stars
new,
burn through
even
their
larger
fuel
galaxy, an
quickly
elliptical
and end their
galaxy,
lives
which
as
some have
powerful
nicknamed
supernovae,
Milkomeda.
releasing
It's incredible to
intense
think about,
radiation and
isn't
shock
it?
waves.
Our galaxy is a
A nearby
dynamic,
supernova
living
can
system.
strip a
It's
planet
constantly
of its
moving,
atmosphere,
changing,
or
and
flood
creating
its
new
surface with
stars.
harmful
We are just a
radiation.
small part of this
In
grand cosmic
clusters where
ballet,
massive
living on a
stars
tiny
form
planet,
together,
orbiting
these
an
events
average
happen
star in a
repeatedly
quiet
over
corner of a
relatively
vast,
short time
sparkling
scales.
city of stars.
Then
As
there
we
are
drift
gamma
back
ray
from our
bursts.
journey,
They're
take a
among the
moment to
most
appreciate this
energetic
cosmic
events in the
home.
universe.
Thank you for
When they
joining me
occur,
on this
they
gentle
release
exploration
narrow
of the
beams
Milky Way.
radiation that can travel across vast distances. If one of these beams were aimed directly at a life-bearing planet, it could cause serious damage to its atmosphere. These events are rare, but they tend to occur in regions with active star formation, not in quiet, settled areas like our own. There are also vast clouds of gas and dust that look peaceful but hide intense radiation environments. High-energy cosmic rays move through the galaxy, guided by magnetic fields, sometimes concentrating in certain regions. And then there's the simple issue of materials. Far from the center, there are fewer heavy elements. Planets like Earth require elements forged in earlier generations of stars. Without them, rocky planets are rare and complex chemistry becomes difficult. So life-friendly regions occupy a narrow range. Astronomers sometimes refer to this as the galactic habitable zone, not a precise boundary, but a general region where conditions are more forgiving. Our solar system happens to fall within it. That doesn't mean life is guaranteed here. It means the galaxy hasn't made it impossible. And that balance isn't permanent. As the Milky Way evolves, star formation shifts. Regions grow more active or quieter. Radiation levels change. The boundaries of habitability move. The calm we experience is temporary on cosmic timescales. This understanding adds another layer to the story. The Milky Way is not just a backdrop, it actively shapes what can exist within it. Asking how old the Milky Way is sounds like a simple question. It isn't. Unlike a single object, the galaxy didn't form all at once. It came together over time, piece by piece, and that makes its age hard to define. Some of the oldest stars in the Milky Way formed more than 13 billion years ago, not long after the universe itself began.
B stars are ancient, faint, and low in heavy elements, meaning they formed before many generations of stars had enriched the galaxy with heavier material. But the galaxy as a structured system, with a disk, spiral arms, and a central bulge, formed later. Exactly when depends on what part of the galaxy you're talking about. The halo likely formed first. Stars there are old and move in random tilted orbits, suggesting they were among the earliest to form or were captured from early mergers. The central bulge appears to have formed early as well, possibly through rapid star formation or early collisions. The disk came later. It grew gradually as gas settled into a rotating plane and formed new stars over billions of years. Even today, that process hasn't stopped. So when someone asks how old the Milky Way is, the most honest answer is different parts have different ages. There's another complication. Many of the galaxy's stars didn't form here at all.
As the Milky Way absorbed smaller galaxies, it brought in stars that were already old. That means some stars inside the Milky Way are older than the Milky Way as a unified system. This blurs the timeline even further. Astronomers also run into conflicting data when they try to date different populations of stars. Some appear older than expected based on current models. Others show chemical signatures that don't quite match the predicted history. These mismatches suggest that the Milky Way's formation wasn't smooth. It was uneven, bursty, influenced by events we're still trying to reconstruct. There's also uncertainty in how quickly star formation happened early on. Did the galaxy form stars rapidly and then slow down, or did it grow steadily? Evidence points in multiple directions. Even today, age estimates for the galaxy vary depending on the method used. That's not a failure of science, it's a reflection of complexity. The Milky Way is a layered system, built over immense spans of time, with parts forming, merging, and reorganizing independently. Understanding its age isn't about finding a single number. It's about understanding a process that unfolded over nearly the entire history of the universe. When you look at the night sky, the stars seem predictable. They rise and set. They keep their patterns. They feel fixed. But when astronomers track stars carefully, their speeds, directions, and compositions, some of them don't fit the rules we expect. One example is hypervelocity stars. These stars are moving so fast that they're escaping the Milky Way entirely. Their speeds are far higher than normal galactic rotation can explain. The most likely cause is a close encounter with the supermassive black hole at the center of the galaxy. When a pair of stars passes too close, one can be captured, while the other is flung outward at extreme speed, sent racing into intergalactic space. These stars won't return. They'll drift alone in the dark between galaxies for billions of years. There are also stars that appear older than they should be. Some have extremely low amounts of heavy elements, suggesting they formed very early in cosmic history. Yet they're found in places where we don't expect such ancient stars to survive undisturbed. Their presence hints at early mergers and chaotic beginnings, stars formed elsewhere, carried in, and left behind. Then there are rogue stars. These aren't bound to any one region of the galaxy. They move on unusual paths, tilted far above or below the galactic plane, sometimes even moving against the general flow of stars. Their orbits suggest they were either kicked out of their birth environments or captured from other galaxies long ago. Some stars are doing something else entirely. They're moving in coordinated groups, sharing the same motion through space even though they're now spread far apart. These stellar streams are the remnants of clusters or small galaxies that were pulled apart over time. The stars remember their past, even when their original structures are gone. There are also stars behaving oddly in time. Because of gravity, time passes slightly differently in different parts of the galaxy. Stars closer to massive objects experience time more slowly than those farther away. The effect is subtle, but real. On cosmic timescales, even small differences add up. All of this tells us something important. The Milky Way is not a neatly organized system where everything follows simple rules. It's shaped by past interactions, extreme environments, and rare events that leave long-lasting signatures. When we find stars that don't fit, they aren't mistakes, they're clues. They point to things that happened long ago. Close encounters, violent beginnings, and long journeys across space. And as we follow those clues, we start to see that motion itself is stranger than it looks. Because even the galaxy's rotation doesn't behave the way we once thought. At first glance, the Milky Way seems to rotate in an orderly way. Stars orbit the center, inner stars move faster, outer stars move more slowly. That's what simple gravity would predict. But when astronomers measured stellar motion across the galaxy in detail, that picture didn't fully hold up. Far from the center, stars move faster than they should. Their speeds don't drop off the way basic models predict. This was one of the earliest signs that something unseen, dark matter, was affecting the galaxy's motion. But even after accounting for dark matter, there are still details that don't fit neatly. Some stars move slightly ahead of the galaxy's rotation, others lag behind. Entire regions show subtle ripples in motion, as if the disk had been disturbed and never fully settled back down. These ripples likely came from past interactions, small galaxies passing through, or large concentrations of mass tugging on the disk. The effects are faint, but they're measurable. Then there's the issue of vertical motion. Stars don't just orbit in flat circles, they bob up and down as they move, crossing the galactic plane repeatedly. Over time, these vertical motions can create waves, large-scale oscillations that travel through the disk. It's similar to what happens when something heavy passes through a calm body of water. The disturbance spreads long after the initial event. Near the center, motion becomes even more complex. The gravitational pull of the supermassive black hole dominates close by, forcing stars into fast, tight orbits. Slight differences in distance lead to large differences in speed. In those regions, motion is less predictable and more sensitive to small changes. There's also time to consider. Because gravity affects time itself, stars in stronger gravitational fields experience time slightly slower than those farther out. The difference is tiny on human scales, but over billions of years, it becomes part of the galaxy's story. The Milky Way is not rotating as a rigid object. Different parts move at different speeds. Structures shift. Patterns evolve. This constant motion blurs boundaries and mixes populations. Stars born far apart can end up neighbors. Others drift away from their birthplaces entirely. Understanding this motion is key to understanding the galaxy's past. Every irregularity is a record of something that happened, a merger, a close pass, a burst of star formation. The galaxy carries its history in how it moves. And when we step back and compare the Milky Way to other galaxies, another question emerges. Is our galaxy unusual, or is it just one example among many? From the inside, the Milky Way feels important. It's where we live. It's the backdrop of our night sky. For a long time, it was easy to assume our galaxy must be unusual in some way. But when astronomers began studying large numbers of galaxies beyond our own, a different picture started to emerge. In many respects, the Milky Way is ordinary. It's a spiral galaxy of moderate size. It has a central bulge, a rotating disk, spiral arms, and a dark matter halo. Billions of galaxies across the universe share similar features. When we compare star formation rates, total mass, and overall structure, the Milky Way falls near the middle of the range. It's not especially active, it's not especially quiet. It's not unusually large or unusually small. That ordinariness is important. It means the processes shaping our galaxy are not unique. They're part of broader patterns that play out across the universe. And yet, in some subtle ways, the Milky Way stands out. Its star formation rate is relatively steady. It hasn't undergone a major disruptive merger in a long time. Its disk is thin and well-ordered compared to many other spirals. These traits suggest a comparatively calm recent history. Not perfectly calm, but calm enough to allow long-term stability. This balance may not be common. Some galaxies form stars so aggressively that they burn through their gas quickly. Others are disturbed repeatedly by mergers, never settling into stable disks. The Milky Way seems to have avoided both extremes. It also has an unusually massive satellite system relative to some galaxies of similar size. The presence of nearby dwarf galaxies provides clues about its past and future interactions. Another interesting detail lies in timing. The Milky Way formed at a point in cosmic history when conditions were favorable for building complex structures. Earlier, the universe was more chaotic. Later, expansion and energy changes may slow galaxy growth. In that sense, the Milky Way may be neither early nor late, but well-placed in time. Whether this matters for life is still an open question. When people talk about life in the galaxy, they often focus on planets, but planets are only part of the picture. The larger environment matters just as much. Life needs time. It needs stability. It needs a steady energy source without constant disruption. Not every part of the Milky Way can offer that. Closer to the galactic center, stars are packed tightly together. That increases radiation exposure and the chances of nearby stellar explosions. Planetary systems there are more likely to be disturbed over long periods. Farther out, the problem changes. There are fewer heavy elements, the materials needed to build rocky planets and complex chemistry. Stars there tend to be older and surrounded by thinner disks of material. Between these extremes lies a broad region where conditions are more balanced. This is sometimes called the galactic habitable zone. It isn't a sharp ring or a fixed boundary. It shifts over time as the galaxy evolves. But it represents regions where radiation levels are lower, heavy elements are more common, and planetary systems have a better chance of remaining stable. Our solar system falls within this zone. That doesn't make Earth inevitable. It just means the galaxy hasn't stacked the odds entirely against us. Even within this zone, many things can go wrong. Planets can lose atmospheres, orbits can change, stars can flare unpredictably. But on galactic scales, this region offers more time for complexity to develop. There's another factor to consider: timing. The Milky Way today contains more heavy elements than it did early on. That means rocky planets are more common now than they were billions of years ago.
But over time, star formation will slow, and some of the raw material needed for new planets will be locked away. This raises an open question. Is life more likely to arise earlier in a galaxy's history or later? We don't yet know. Some researchers suggest that Earth may be relatively early, forming when conditions first became favorable. Others suggest we may be late, appearing after multiple generations of stars enriched the galaxy. Either way, the window for life is not infinite. It opens, it changes, it eventually closes. The Milky Way provides the stage, but it also sets limits. And while the possibility of life elsewhere is fascinating, it also highlights something else. Despite everything we've learned, there's still a great deal we don't understand about our galaxy. After centuries of observation, it's tempting to think we have the Milky Way mostly figured out. We don't. Some of the most basic questions about our galaxy are still open. We don't know its exact mass. Estimates vary depending on how far out you measure and how you interpret star motion. The difference between those estimates is large enough to change how we understand the galaxy's influence on its surroundings. We don't know where the Milky Way truly ends. The visible disk fades gradually, but the dark matter halo extends much farther. How far it reaches and how sharply it tapers off is still uncertain. We don't know what dark matter is made of. We know how it behaves gravitationally, but not what it actually is. Until that question is answered, any model of the Milky Way remains incomplete. We don't fully understand how the galaxy formed its structure. Why does it have the spiral pattern it does? Why is the bar shaped the way it is? Why do some stars move in ways that don't match simple predictions? We don't know how often the central black hole becomes active or what triggers those periods. The evidence suggests it has flared in the past, but the details are unclear. We don't know how common galaxies like the Milky Way really are. Surveys give us estimates, but every definition of Milky Way-like depends on which features you consider most important. We also don't know how the future will unfold in detail. We can model mergers, star formation, and long-term evolution, but small differences grow over billions of years. The farther out we look, the fuzzier the predictions become. These gaps in knowledge aren't signs of failure. They're signs that the Milky Way is a complex system shaped by forces acting across enormous scales of space and time.
Each unanswered question points to something deeper. And that brings us to the end of this journey, not to a conclusion, but to a perspective. Because the Milky Way isn't something we've mastered or finished understanding. It's something we're still learning how to see. And that leads naturally to one final thought, not about facts or measurements, but about where that leaves us. The Milky Way doesn't announce itself. It doesn't feel vast from the inside. It doesn't feel ancient. Most days it feels like nothing at all, just a dark sky with a few familiar stars. That's not because it's small. It's because we're embedded in it. Everything you've heard in this story, the size, the motion, the history, the uncertainty, is happening around you all the time. You're moving with the galaxy as it turns. You're carried by gravity you never feel. You're surrounded by structures you'll never see directly. And that's normal. The Milky Way wasn't built for observers. It wasn't shaped to be understood easily. It's the result of gravity working patiently over billions of years, assembling and rearranging matter without concern for perspective. From the inside, even something enormous can feel ordinary.
That's why understanding the galaxy isn't about memorizing numbers or diagrams. It's about accepting scale. The idea that some systems are too large to grasp all at once and too slow to notice in a lifetime. Every star in the sky has a history longer than human civilization. Some have been shining since before Earth formed. Others will outlast the sun by billions of years. The atoms in your body were forged in stars that lived and died long before the Milky Way looked the way it does now. In that sense, you're not just inside the galaxy, you're made of it. And while the Milky Way will continue to change, merging, drifting, reshaping itself, none of that is urgent. There's no countdown, no deadline. The galaxy is patient. It has time. So as this story comes to a close, there's nothing you need to do with this information, nothing to solve, nothing to hold on to. Just the quiet understanding that the place you call home extends far beyond what you can see, and that being a small part of something vast doesn't make you insignificant. It just places you inside a much larger story, one that was already in motion long before you arrived and will continue long after. And for now, that's enough. And that's where we'll pause. Not because the story of the Milky Way is finished, it isn't, but because this is a good place to rest. The galaxy will keep turning either way. Stars will keep drifting. Nothing here is in a hurry. If this series helped you see the Milky Way a little differently, not as a picture in a book, but as the place you're actually inside, then you might enjoy continuing this journey. You're welcome to like the video if it felt worth your time. You can subscribe if you'd like more quiet stories like this, slow, grounded explorations of science, space, and the bigger picture we live in. And if there's someone you think would enjoy listening to this at night, feel free to share it with them. Before you go, I'd love to hear from you. What part of the Milky Way stays in your thoughts the longest? The size? The unknown matter? The black hole at the center? Or the idea that we're just passing through a much larger story? You can leave that in the comments. For now, thanks for spending this time here.